And if Dr. French walks in, everyone, we started at 5:31.
All right, so thanks everyone for coming and the faculty for having me here. As Dr. Gallagher said, I am an automation engineer, and this is going to be my presentation. So this is the seminar's agenda. I will introduce myself and provide some background of who I am. I will talk about my college career here at SUNY Oneonta and at NYU. I will also talk about my projects that helped me get into NYU and other my work. And then I will talk about my professional career as a whole and the things that I do at work. So as Dr. Gallagher said, I began school here at SUNY Oneonta with a bachelor in physics, and I graduated in 2019. Then I went to pursue mechatronics and robotics at NYU and graduated at 2021. And I'm currently working at biodiagnostics as an automation engineer. I'm still there as far as I'm concerned, you know. So background. If the accent so far did not give it away, I was not born in the United States. I was born in Lima, Peru, and I actually grew up there. I spent most of my life there, and I moved to the US when I was 16. So this means I went to primary school, secondary school there, and things were very different than here. In San Roberto, although it's a Catholic school, it had a big emphasis in science and technology. That's actually the first time I was introduced to Microsoft Office, Photoshop, and Microsoft Word and other stuff like that. Actually, funny enough, they also had English classes there, and that was a lot of the classes that I never tried. So I was always sleeping in that class, never really pay attention, because I thought I'm never going to use English. No one here speaks it. There's no purpose on it, and I'm not going anywhere. And then that backfired really bad a couple of years later. So my interest in science, although I know my teachers in Peru try really hard to make it interesting, I never really got it from school. I actually got it from things from my childhood. So one of those things was early exposure to machinery. At my dad's factory, he had a bunch of machines that just cut nails and also combine rods. And I was really excited to see that, because as a kid, it was just a big machine, just moving pieces around. So that got me interested into technology. Another thing was trains. It's just a big machine. It was pretty cool to see it run full speed on the rails. Also building blocks. I had a bunch of Lego-like blocks, and I used those blocks to build robots, but they did not have any software or anything like that, or any electrical component. They were just building blocks. So I put a lot of those together, and that was really fun. So to me, science was a lot of fun, especially early in life. But I really got inspiration from video games and anime. So video games and anime was what really got me into science, just to see the amazing concepts that they display. So going off that, so these are the shows that actually got me into science. I remember Metabots being a big thing back then. And if you really look at it, it's just a humanoid robot with a built-in AI, with its own personality. And it's amazing at fighting too, which made it cool. Hey, Dr. French, long time no see.
We started at 5:31.
What?
We started at 5:31.
You did?
Yeah, that's for now.
You started at 5:30. So that means you already didn't start the tape? Did that start the recording?
Oh, did you press mute?
Oh, I did press on mute.
So you're unmuted, right?
Yes.
Okay.
So yeah, so it was cool to see these amazing robots just fight, and I'm hoping that one day we can actually see something like that. Maybe not fighting, but just human and robots walking around. Another thing was Yu-Gi-Oh. I grew up playing the card game. I suck at that card game, pretty bad. But the concept behind it was amazing. Just put a card on a disc, and then you get the monster right in front of you. Now with augmented reality, that's almost we're getting really close to see something like that. Konami has put a lot of money into it, and now that show that's in fiction, it's almost a reality. So many things like that. Zoids is a great show, just big robots fighting again. So I actually managed to find 2 pictures of my younger self working on science projects. So in the first picture, I built some sort of circuit. I can't recall what it was. And then on the second picture, I built a city block or replicated a city block. And these were things that I was happy to do back then, especially as a kid, because I thought it was fascinating to work with electronics and robots to hopefully one day see those animated shows become reality. However, as time went on, that excitement about science really faded away. And honestly, that was because school kind of turned into a chore. It was mainly a hassle to learn about science rather than exciting and fun. So although I know that the teachers in Peru did their best at trying to encourage people to do it, it really just pushed me away from it because it wasn't never about learning anymore. It was just about completing the homework, passing the class, and then just move on to the next thing. So with that being said, as my passion for science faded away, I actually moved to the US about the same time. And when I first arrived to the US, things were very different here, just not the culture, but also the way science was taught. So for instance, in Peru, there was a lot of linear thinking and an emphasis in memorization. So it was never about thinking what the problem was. It was about memorizing the concept and just memorizing step 1, 2, 3, and solve the problem. It was a very straight path. And in a way, that's kind of what companies wanted at the time, just someone who knew what was happening and someone who knew how to solve it. And it wasn't anything out of the ordinary. In the US, on the other hand, in high school, there was a lot of focus on discussions. So they would ask, so why did this happen? If you have the same problem in a different situation, would the same thing happen? And it focused a lot of interaction with your peers and to talk about things that you wouldn't normally think, especially if you interact with other people, right? They have different ideas. And then another thing that the US is amazing is innovation. There is a lot of emphasis to jump into the unknown and find out things that haven't been discovered. So this is something that the US really shines at. And that's actually what got me back on track on science. And also the massive infrastructure that there's in the United States, like this lab, the school here. The first time I went to Times Square, I thought I was hallucinating, all the lights, amazing buildings. So it was incredible to see something like that, to be real. So with that, I actually got I got back into science and I wanted to pursue it again. So with that, I decided to come to SUNY and pursue a degree in physics because I wanted to understand how things work and the why of things. And I just gotta say that this is an amazing school and you guys are getting a great education. The faculty here are amazing. And I'm not saying that because they invited me here, but it's a really great school. The town is charming, there's a lot of events, and above all, it's a great place to be at. The classes that you're taking, they are preparing you to take challenges in graduate school as well as in your professional career. So there's a lot of classes you can take at SUNY Oneonta. And a few the classes that really helped me the most are these, especially since I took a path in robotics. So the first one is fundamental of programming. That class, obviously, if you are going to work with robots, you gotta know how to code. Then you have computational physics. This class was actually really hard. Barely passed it, I think. But for fundamentals of programming teaches you and gives you the knowledge about coding. And computational physics gives you a purpose to use the tool that you know. So this way you learn how to simulate things using physics equations and yeah, generally that. And then we got linear algebra. So linear algebra teaches you about matrices. And if you work in robotics, especially with path trajectory, we're going to use them a lot. It's a lot of matrices, especially if you want to use forward kinematics, inverse kinematics, you're going to use them all day. And it gets more complicated as you go, but linear algebra will give a great foundation. Then you have electronics and circuits. Actually, I took electronics and circuits with Dr. Fox, and it was actually the one class that gave me a great insight to what work would be like. And so actually, I have a story about it. So when I took your class, Dr. Fox, I remember the exams were one-on-one with you, and we had a circuit set up, and you would ask questions about it. You would ask us to troubleshoot. So now that kind of became what I do now. But now instead of you, imagine the board of directors watching me troubleshoot. It was one day we had to showcase one of our automated machines, right? So I had to get it running. So I go there, set it up, and I ask one of our automation technicians, just run the machine and make sure that it works. If something happened, just call me. So I get a call a few minutes later, and he goes like, "Hey, yeah, man, the product is getting rejected. I don't know what's happening." So I go back, I start, adjusting things, making sure everything is connected properly. And ideally, I wanted to test what I did to make sure it worked. But as I'm finishing up, I see them walking in, and I'm like, oh God. So I close everything, and they ask, like, is it ready to go? And I go like, sure. So I click start, and thankfully everything worked. And at that moment, I was probably, no one on earth had more faith in God than I did. You can be assured that my faith rival Pope Francis. I was the first one in Mass that Sunday. But yeah, it was, having to also explain what I did and how the machine worked to first Dr. Fox and now the board of directors was great. So this class, for instance, will give you a good insight of how you can do things, what you will do at work as an automation engineer. So there are many lessons I learned through the classes I took, and there are many more in the physics classes that you'll take. But the two lessons that I really stood out to me was how to bound problems to assumptions. And this is because if you notice in your exams or homework problems, you'll realize that they give you situations. So an object traveling at the speed of light, a hollow object, a light behaving like wave. So these things bound the problem to a condition, and based on that condition, you can troubleshoot or solve the problem. Otherwise, it would be a little ambiguous to solve the problem. And then another thing is understanding concepts and not memorizing them. In robotics, and especially with the machines I work with, there's too many components, electrical, mechanical, software, and so many things are running at the same time that if I try to memorize everything by heart, it's just going to be impossible to remember everything. But if I understand what's happening at the moment in which process the machine is at, then I'm able to derive a assumption or conclusion, and this helps me troubleshoot the problem or do an update to the machine. So let's move on to the next one. So with these lessons learned, I think the one class that really helped me decide, okay, I'm gonna do robotics with my career was working on the robotic hand. So thanks, Dr. French, for helping me with this project. So once I finished this project, I knew that I wanted to work with robotics, and that's what I wanted to do. And it was actually very interesting to build it. I used Lego Mindster Kit. So you can see it's just made out of Legos. And the software is actually quite simple. If you press the button right here, the hand moves into this direction, and then you release it and it goes back to its original position. So the whole purpose of this hand is to just replicate hand movements and to move objects from one place to another. But doing this, I actually had a lot of fun. And if I have to go back to one point in my life where I said, all right, this is what I want to do, it would be this, when I completed this project. So with that said, after I completed that, I knew that I wanted to pursue robotics, and I decided to go to NYU. And when I went to NYU, there was a few things that I noticed. So the first thing, it really taught me what robotics was. It's, in simple words, it's just design, building, and programming electromechanical systems. And you can go into many branches of robotics. You have AI, 3D design, machine learning, computer vision, simulation. So you have a wide range of possibilities, and in this area is still in its infancy. So you can it's gonna keep growing. So it's a great area to get into. And actually, a lot of the schools have their curriculum based around simulation. So a lot of robotics schools will teach about simulating things rather than actually building something. So that's what I liked about NYU's program. It had an emphasis on physical prototyping and entrepreneurship. So they wanted you to build something and then hopefully market that product. So that was one of the focus of their curriculum, but something that they really stressed was addressing a meaningful problem. And this is because robotics shouldn't be about just building a cool machine or just building something for the sake of building it. It should be geared towards solving an issue to help people or to address something that is affecting an area or just the general population. But to address a meaningful problem, we first have to learn the basics of robotics. And the way they did it was they taught us mechatronics, which is basically prototyping. We learned about different circuits, sensors, motors, and we were given challenges. We had to put something together to pass that challenge. Then we had foundations of robotics. So this class will teach you the math and theories of robotics. So this is where you apply a lot of the matrices. And it gets quite complicated, but it's once you get through it, it's not that bad. Then robot perception is basically machine learning with computer vision. And it's the way the robot perceives its environment, whether that is with a push sensor or with the camera. You can program that and make the robot act in a way that you want it. And then you have simulation tools for mechatronics and robotics. What this class does is that it takes foundation of robotics. So it takes all the math and theorems, and then you apply it to simulations. So you create robotic arms going from point A to point B. Then you can also do feedback loops. And it teaches you all sort of stuff that you can simulate rather than prototype. So with this class, with all the previous classes, I was taught the basics of robotics and what I could do with it. But the one class that really shined about addressing a meaningful problem was robots for disability. This class introduced me to a lot of cognitive and physical disabilities that people go through. And it's actually heartbreaking to see that people can just go about their day as usual and then their life gets upside down just by an accident or by just really some sicknesses that are hard to detect. But this class also showed me that there is technology and people out there working constantly to help these people. So for instance, we have this is a picture of an elderly, and this is a robot that goes around and helps them, checks on them. You can connect with them in case they need someone to talk to. And so there is many more situations with this and many more robotic solutions. One of the coolest robotic solutions I saw was some kind of eye for people who lost their sight. So they can put a chip in your eye and then you are not able to see it, but you can see shapes like in black and white. And that's pretty cool. So at least you'll be able to tell, okay, that's a building. This blurry thing is a car that's coming towards me. So it's pretty cool that people are going out there and making a difference. So based on this class, I was also forced to come up with projects that would address disabilities. So one of those was the robotic hand simulation. So it was basically this guy, but simulated. So no motors were burned. Everything is, yeah, I didn't burn anything. So as you can see, this is a 3D design, and I used MATLAB for this. So this is probably something you guys can do here too. The whole purpose of this is to simulate human hand movement. I basically use a 3D design that got imported to MATLAB. And based on that, then I just use the joints and sine waves to replicate finger movements. And this way, if someone ever loses their hand, you can 3D print this and then they can replace their hand. And this is the base model. You can actually, if someone really wants to, you can actually attach that N effector to another bigger robot. So now you can do more things with it. So it's always good to expand on it, but that's what I did initially. Yeah. So another thing I did was a steering system for people with upper limb amputations. This project was basically designed to help people without arms to drive cars. So actually, I think this video has volume.
Now, FPT Jose will demonstrate the driving system. Press shift, which will calibrate the accelerometers. Press brake. Press gas. All right, turn right. Turn right. Right, turn left. Right, right signal. Right, left signal. All right, so now Jose will practice route driving. Go ahead, Jose.
All right, I'm going to change.
So I can take you to this part of the video where I'm going to drive through a narrow street. And the way this project worked was we had gyros on my shoulder, and we used an Arduino board to control these gyros. What we basically did was we set thresholds for the movement of my shoulder. And for instance, if I wanted to use the blinker, I would say, if this movement is beyond this threshold in the X direction, turn on the right blinker. And if I wanted to go left, I would say go up. And if it was past the threshold, I would, then the car would turn right or left. And it's actually a pretty nice system. The first time I did this, I was having too much fun, and I was driving like a maniac, like in GTA. And I don't know what was wrong with me, but I sent that video to my professor, and I thought the prototype was not working. So this is like the retake where I was driving like a human being. So yeah, it's a cool project that hopefully can give you an idea on what you can do for your driveway courses or even here at SUNY Leonta. All you need is cardboard, gyros, and just push sensors, really. That's what we use for the pedals. So the biggest tool.
Did you think that the shoulder motion was the best way for interfacing with that? Or what about voice activation? Do you think maybe that could be better or not good?
We thought about it, but we were thinking, what if you have someone in the car and you wanted to have a conversation?
Yeah.
Then you could trigger something, and so we decided to go with that because ideally you would be sitting down, with the seat belt on. Yeah, but we thought about it and we said, well, if they wanted to talk, it would be a little hard.
Okay.
Yeah. So moving on to the next thing. So once I completed that class, I started my professional career in biodiagnostics, and I became their automation engineer. So my responsibilities there are to maintain the vision system, on-site support, software updates, and machines improvement. Actually, fun fact, when I took robot perception, that was probably one of the hardest, I think that was the hardest class I've ever taken. It was so difficult, and now that's what I do for a living. It's actually really ironic. So this is the machines that I work with. This is one of our latest models, and this is one of our smaller machines. They are called LFTA. That means lateral flow device assembly. What that means is that the product comes, let's say, from point A and just goes straight down to point B. There's only one flow, kind of like a river, just goes downstream. And if we take a closer look at these machines, I can show you the robots we use. So this is the FANUC robot, and this is the SCARA robot. They're actually both pretty good, but the FANUC robot are actually really amazing. They are very consistent, they rarely stop, and they are industry standard. So if you have the chance to work with them or learn about them, it's gonna open a lot of doors for you, especially in the robotics field, because they are used by many companies and they're extremely reliable. Expensive too, so don't break them. Then you have the SCARA robots. These are also pretty good for what they do. Not as consistent as the FANUC robots, but the main goal is to basically just move things around. And they do that with path trajectory. If you're designing this, you're gonna use a lot of equations. You're gonna use also computer vision to help the machine know where it is. The work area of the robot, it's extremely important. You don't want any of these robots just going beyond a safety point, otherwise they could hurt someone, especially this big guy. It's extremely discouraged to bypass the sensors, because if the robot does not know you're there, it will not stop, it will just hit you. So it's always really relevant to have the safety sensors on. And yeah, so it's pretty cool. You have 1, 2, 3 motors right there, and they all work together to make the magic happen. And besides just path trajectory, which is using equations, we're gonna combine it with vision inputs. So it's pretty cool when everything comes together. And speaking of vision systems, the vision system we use is called Cognex Vision System. It's basically a software that lets you use different tools for computer vision. Obviously, this is not a picture from the company. I'm not allowed to show that, but you can find that picture online. But this software, what it basically lets you do is use tools right here for anything that you want to do with the picture. You can use machine learning, train a tool to recognize a picture. You can recognize edges on a device. You can recognize marks if you want to. You can even create access points, so you can have a reference frame in different locations. And then, what's the purpose of all of this? So the purpose of all of that is to have QC inspections in different parts of the assembly product. So you have to make sure that when the product is coming from point A to point B, that everything is on point. Everything that should be on the product is on the product. Things can go sideways, and the next thing you know, like 2 parts are missing and nobody knows where they went. So the machine, by using the vision system, you can ensure that everything is in check before it goes to the next stage. And yeah, and you can do a lot with it. You can actually even create your own tool, I think, with C#. You can actually code it too.
So this is a purely visual-based system that is medical grade, used in the medical field.
Yeah. And you can actually, I think, if you go to our website, they might have training tutorials. A lot of company uses that, so it will expand your career opportunities.
Does it need to be in a sealed box container out of the elements? Because I know visual is kind of hard to make accurate.
Yeah, so the way it works, I guess generally speaking, because I know there's, I think there's a few things I can say, I know that, but generally speaking, we evaluate different aspects of the product at different stages. So we evaluate the product at smaller parts. So once that small part is checked that it's good to go, then you go to the next step. We never evaluate it as a whole. We do that a bit very, very last, just in case something went wrong. But yeah, as you said, it's very hard to like get it down perfectly. But if you get it to be as consistent, then it should be okay. It's like 99% of the time it's okay.
So it's just a really close line to apart.
But yeah,
Mine's is just very close to the park.
yeah,
Small park.
in a way, yeah. But yeah, so it's a powerful tool to learn. And another thing that I do is on-site support. So my job is not only to keep the machine in good shape, it's also to help the automation technicians and mechanics with robotic issues. So throughout the day and when the machine is running, you will find a lot of software issues, glitches, problems, motors burn, sensors get messed up. So it's important to maintain and keep the machine running. So I actually got a lot of hands-on experience. If something is too hard, especially mechanically, the mechanics do it. I just do the basics, and I actually watch them work when they change motors and sensors, because you can actually learn a lot by just watching, and they have obviously their mechanical experience is exponentially better than mine. So, but by watching them, you learn what to do for the next time something like this happens. And also, it's something funny about robotics that they just display bizarre behavior. It's never, it's so weird, it's never the same. For instance, right? If you make a script and you have step 1, 2, 3, 4, 5, the robot should go 1, 2, 3, 4, 5, right? But it doesn't, it's weird, it's so odd. It's like, so I told the robot one time, go from point A to point B, and it just wouldn't do it. It would just go to point C, straight to point C, and I just couldn't get it to work. So I called the beam mechanic, say, hey man, I cannot fix this problem, can you come take a look at it? And he walks in, and as soon as he walks in, the robot fixed itself. It started just working like normal. And like, it made me look like I was crazy, you know? But it also happens to other people, of course, that, you know, just the robot goes nuts for like a second and then just goes back to normal. And this is again due to, there's so many scripts and so many electrical parts there that something just gets a little out of whack, then just cause a whole ripple effect. And another point is that machines aren't perfect, and they will require modifications. A lot of times in robotics, something looks amazing on paper, but once you apply it, it's actually, you know, pretty bad. So we have to go back and do something, make a theory, test it, and then see how it reacts into the real production, and then go back to the drawing board if that doesn't work, and so on. Nothing for robotics, at least in my experience, nothing that is on theory perfect will work well with machines. It always requires to go back to it and tweak it a little bit, modify it. So there's a lot that goes into it. So with this, with a lot of troubleshooting, I also do software updates and machine improvements. And for the software updates, you know, feedback is key. There is a reason why companies want your data. It's because whatever you are using, it's useful to them to improve their algorithm. And the same thing happens with these machines. I'm not there all day with the machines, but the automation technicians, the mechanics, they are there all the time. So whenever they tell me, I have this problem, this happened, I have to take it with a lot of consideration, because this can make the machine better, this can have more runtime. So it's really important. Their feedback is crucial. And actually, based on their feedback, I was able to create quick access test notes. It's just with the click of a button. I remember they have to troubleshoot a lot, and to get to the test notes, you have to navigate through the software, and it can be time consuming. And sometimes I actually forgot to turn it off once, and then the machine obviously during production wouldn't work. So until someone came up to me and said, hey, can we just make a button turning on and off? And then, yeah, and then I did. That solved like a lot of issues. It sped up the troubleshooting process, also redesigning some parts. We had problems with our vacuum system, where a lot of times there was too many debris inside the vacuum tubes. So we had to take it apart, then clean it, put it back, and then keep going and hope it works. But then by creating another button to manage the vacuum system, now they're able to troubleshoot it within like 5 seconds. So getting their feedback is important to me, because it helps me make the machine better, which ultimately leads to them having a better time with the machine. And with these software updates that I gotta interact a lot of with programming languages, I'm here to tell you that it doesn't really matter which one you learn. I spent a lot of time researching which programming language to learn for robotics. It really doesn't matter. They're really pretty much the same. I remember spending a lot of time just going back and forth programming languages just to trying to find the perfect one for robotics, but there really isn't. Whichever you pick, it's gonna be fine. For instance, the Fanuc robots, they're used across the entire industry and they have their own programming language. So it's not even like, MATLAB, Python, they won't help you with Fanucs. You'll have to start that from scratch. But if you want a programming language for robotics, C++ tends to be the go-to for robotics. So if you know how to do C++, then you'll be fine. If you want to do rapid prototyping and simulation, Python and MATLAB. Python for quick prototyping and MATLAB for simulation. So those are also used for robotics, but they are never used for the final product. They are used for just quick prototyping. C++ tends to be in the final product. So that's it. With that said, so with all of the responsibilities for my job, what's the mission for automation? What automation is trying to do is basically drive down cost, increase production, and accelerate manufacturing. And all of that can be embodied with this tree right here. So we need to increase production, so more things need to come out. And sometimes it's hard for people to work 24/7, but a robot can do it. And obviously robots can work a lot faster than people can. But the way to do it, and the way I think, and personally, the way to look at it, I think it's this. So imagine the branches of this tree are different processes throughout the manufacturing process, right? So within this branch, you have two steps. When step 1 and step 2 are completed, they combine into one point. And that's where the inspection happens. You have to make sure that step 1 and step 2 were completed. When you check that, they just move down the line and so on. But at the same time, you have other processes happening at the same time. And all of that just gets combined into at one point here, and that's where the final product comes out. And this way, you accelerate manufacturing and increase production because you have multiple processes happening at the same time. So this drives down cost, increases production, and accelerates manufacturing. So that's, as an automation engineer, that's my mission, to ensure that these machines are capable of doing that and to hopefully get the company to be more profitable. And that's, I just wanted to say thanks for your time and thank you for having me here and for coming. It's been great. Thanks, guys. Any questions?
When you were, so you need to develop in your master's program projects that students need. Is that difficult to come up with ideas for things to do?
Yeah.
And how did that process go?
Yeah, it was pretty difficult. My friend and I just sat down and started brainstorming, just looking up the PDF. So our professor gave us a PDF with the lessons. So we were browsing through the disabilities that there were, and we were just saying like, okay, what can we do about this one? This seemed too complicated. So we went back to looking at another disability and just brainstorming, talking to each other. They came up with that idea. But yeah, it was pretty difficult, because we also wanted to be innovative, but it's kind of hard now. I feel like pretty much everything has been invented. So I might have been born too late, but yeah, it's just talking to each other, going through the PDF, brainstorming. That's how we got the ideas.
You have a test room in your job
Yes.
to to make your robots, make sure the code of your robots functions?
Sadly, no. A lot of the things I do are on the robots themselves. And so what I do first, if we are running in manufacturing, obviously at first I couldn't do it because I didn't have enough experience, but I would watch someone who had more experience do it. So once I knew what they were doing, if I run into the same problem, I kind of already knew what to do. But if it's something completely new, although it's hard, but I have to pause the manufacturing process and test what I did. And although it causes some downtime, it's necessary because if I just do an update and that doesn't work, it jeopardizes the product and the quality of the product. So, so it's tough. Ideally, we would have one, but yeah. So I just do it on the machine themselves, and I have to be careful to not break it because.
Make small changes.
Huh?
Make small changes.
Yeah. So I have to start small, and then I just build up to bigger changes. Yeah. Like we had like one problem once where, as I said, like the robot should go from point A to point B, right? It should stop before, I guess, going too far out of the safety area. But the robot wouldn't. It would just go and slam the door. So thank God no one bypassed it because that robot would have hit someone if they bypassed the safety. So the robot shouldn't do that. And that happened because a motor got discalibrated. So I couldn't just release that robot without testing it. If I did, the robot could just break something or could break itself. And so what I did was I had to stop manufacturing, calibrated the robot again, and then tested it for I would say like about 15 minutes to make sure that it's behaving as expected. And then once that happened, I released the robot and said, okay, resume manufacturing.
So when those situations happen where you have to like have someone come and help you with something that's happening with one of the robots, or let's say like a mistake was made, was it like sort of an environment that promoted that you learn how to do it, or was there like a lot of pressure on getting it right very quickly?
You guys are asking tough questions. So there was both. So the guy that I worked with, he was very open about it. He would let me try first. He was supervising me while I did it. So he always encouraged me to try before I asked for help. So I would try to solve it. If I couldn't, he would step in and help me. So he was very open about it. A lot of the mechanics that I work with, they were also said, try it. I'm here watching you, so nothing bad's gonna happen. But there was a lot of pressure for sure that, when something stops in manufacturing, the company's losing money for every minute that the machine is down. And yeah, it can get pretty stressful because, they're losing money and, I'm there for the opposite reason, to make them money. So it can be pretty stressful at times, but it gets better with experience. Once I tackle a lot of problems, I feel more confident on what I can do. Actually, the first time I had a problem with the vision system, I spent 5 hours figuring it out. So the entire machine stopped for like 5 hours. It was awful because people were coming like, is it ready yet? I'm like, no. So I kept troubleshooting and it didn't seem like 5 hours either. It seemed like 2 hours at most, but they were asking like a lot, like, hey, is it ready? When is it gonna be ready? And that is stressful, It took me 5 hours to figure it out. But then once I got it, it takes me like 2 seconds now. So it got better over time.
Is there a reason that you wouldn't have multiple robots to be able to like fill the position of one that's malfunctioning or behaving rather bizarre, as you put it, so that instead of stopping like that one case where that robot was offline for over 5 hours, that's obviously a lot of revenue that the company is losing. Is there a reason that like, is it just like the problems that occur are just so minute that they can be fixed rather fast, so there's no really need to want to try to have another robot to possibly take its place in the event that something goes wrong?
Well, there's one instance where we did replace a full robotic arm, but in most cases, taking out, let's say, even a small camera, it's going to be a very troublesome, because even when I had that problem, just taking that out requires me to recalibrate the camera or the robot, the motors. Then I have to recode them. I have to connect both motherboards to the software, and then I have to make sure that the electronics is properly wired. So I think it's in like the one case I found, it was necessary because the motor was just dead. There was no way to save that motor, but there's more possibilities that something will go wrong if I just replace the entire thing rather than actually troubleshooting, because there is times where you can actually save the part and just keep going. So there tends to be, there tend to be some software problems at times, but those might take a little time, but you can save the mechanical part and ultimately save money too. So yeah, ideally you want to find out what the problem is instead of just replacing the whole thing.
So you mentioned visual observation by the machine for physical detection, right?
Mhm.
So it sounds like the problem of having very slight changes to lighting and stuff like that can actually be a big problem with your calibration.
Yeah. The lighting definitely affects how the machine sees things. So before the machine actually enters production, I have to make sure that the cameras have the proper lighting. Otherwise, they'll start acting up, and once that happens, the product gets rejected. So I have to make sure that everything is properly set before running it. Yeah.
So how did you find this company? When you were at NYU, you transited to work for them. Like, how did you locate them in the first place?
LinkedIn, I was going through LinkedIn and applied to many jobs, a lot of jobs. Actually, it's funny. The first time I found them, it was, I sent my resume to a recruiter, and then she said, oh, they have this position here. Would you like to try it? It was for automation technician, actually. And I applied for that position, and they said no. So I was like, all right, well, so I went. So then I get a call back like a week later, and they said, we have an automation engineer position here. Would you like to interview for that instead? I said, sure. Went in and got the job. I don't know. I just applied through LinkedIn recruiters. They'll probably contact you through email. If you guys don't have LinkedIn, sign up. There's a lot of opportunity there.
Did you find that your undergraduate education and your graduate education, do they have a similar difficulties, or is somebody who doesn't get every perfect A in undergrad should never go to grad school? What's the secret to success besides the courses you
So to be frank, I know the classes here were challenging, but when I went to NYU, they were exponentially challenging there. And the people there that I found were also like really off the charts. One of my actually classmates, Andreas, he was top of the class, and I really admire him for always being great with homeworks and pretty smart. And but I found at NYU a lot of people that were really like way beyond what I could do. I remember I met this guy. He went to, I think it's Stanford, and he had 5 years of experience. And when we had to do projects, he made it really clear that he was way beyond everyone else. Like, he could answer all the questions. He knew what to do, how to code everything. He was just like, but the good thing is that through those challenges and working hard, especially with classmates, I had this thing where I tried to learn everything and tried to do everything by myself. That was not going to get me anywhere. The way I actually got through school was I had to hang out with the people who were a lot better than me. And I learned a lot from them. My friend Luke, who helped me with the project, he was amazing at coding and prototyping. So I actually hang out with him to learn what he knew, and all of my other classmates too. So working with them helped me get to their level. But one thing I would say is that due to the nature of the physics classes here, I had an easier time understanding robotics concepts. So I understood the mathematics and theorems faster than they did. They had an edge on me when it came to mechatronics and prototyping, but when it came to theory, I would say better than they were. But with practice and talking to them, I was able to overcome that gap in prototyping and almost rival them really. But yeah, so classes, at least for me at NYU, were extremely challenging, but hanging out with the right people helped me get to that level where I could do it myself too.
Thank you.
Any other questions?
Just, I guess there's something on my mind about these robots. About how, like, they're saying, you know, the robot has some code in it. It tells the robot maybe where its arm is or something like that. And then if things aren't calibrated right, then maybe the arm can go too far, right?
Yeah.
So I would have thought that these robots would, in addition to having the code and saying where the arm is, that there would actually be some sensor for real, so that you would know for real where the arm is, so that there would be a fail-safe or something, or some kind of feedback.
Mm-hmm.
How come we don't have something like that?
Well, so technically, once the robot has its own trajectory, we give it like a few more offsets, and that's basically like a boundary. So if the robot's supposed to go to, let's say, take one step right, you say, okay, take that step and add one more step to that. So you go to that, but once you hit that point, it shouldn't go beyond that point. It's not programmed to do that, but sometimes it does. They just really display like really bizarre behavior at times, and it could be due to mechanical problems, sometimes electrical, and checking that is important. I know that, for example, some of our motors, they would just overshoot if the motherboard just went like something brighter, they would just overshoot. So in theory, they are meant to stop at that point, but if something goes wrong, then the robot tends to just misbehave.
Sort of along those lines, it's kind of, I guess the company has done the calculation, but you think that, I'm just imagining that they would do a calculation regarding how much downtime they expect. They give a couple of different scenarios, and one of them might be to have another machine available to sort of replace the one that's not working. And so I guess it's the amount of downtime times the cost of that downtime. The frequency of that happening that will determine that based on the cost of having additional machines and also downtime to calibrate. Is that right?
Mm-hmm. Yeah. I think they did the math, but so I think sometimes we get additional downtime on top of that. So that's where I come in, and I really need to address that problem if that happens. But they do have, I guess, in some scheduled downtime there in case it happens. But we don't have that many machines. So if one goes down, it's sometimes a big issue. So, but yeah, I try to do my best to keep them running.
You seem to be interested in the hand of robotics and all that stuff. What made you decide to work on more the chemical side instead of the medical side, and trying to actually create a bionic hand that a person that no longer has one of their arms or can use? Like why go towards more the robotics piece than the human to robotic interaction?
Mm-hmm. That's actually a great question. Well, because I guess initially, I really need to understand how the robot itself works. I don't think personally, I don't think coming out of school, I have like a year and a couple of months of experience. So I don't think I know enough about the robots themselves to really venture on my own and try to build something like that yet. But I think that's one of the main reasons why I wanted to get to know the robot. So I think that's why I decided to pursue something more, mechanical and electrical based. Mm-hmm.
Any more questions? Well, thank you, Jose. I appreciate it. Nice talk, and And great responses too. And questions from the audience.